Hello, everyone. Yeah, I'm happy to see everyone here who got this chance to share this conversation with us today and to take part in our webinar on how AI can be applied to driver development. I know it requires some effort to get here. It's morning for someone, it's a midday for another one, and also we have people joining us from Europe after a hard work day, and we appreciate your effort. Before we proceed, I would ask everyone to type plus in the chat so we know that you are here, so you can hear me, you can see me, and you can see our presentation, what is more important. So I see some pluses are coming up in our chat. Yeah, that's a good sign. It looks like we have some audience that keeps joining us. Hello, Tom. Yeah, nice to see you here. And Katerina also type a plus for okay, I think now we can start diving into the technical details. But first of all, let me briefly introduce who we are. We are Apriorit. We are a cybersecurity software development company. And since 2002, our core focus has been the most demanding areas of software engineering, low-level and kernel mode development. This is what I meant. And with almost 25 years in the cybersecurity field, we have built our reputation on handling the security critical components that many others avoid. Okay. Thus, welcome our today's speakers. Here with us, Victor Mylokum. Victor is our engineer. Yeah. Hello, Victor. Victor is our engineer and director with more than 2 decades of expertise in this field. And yeah, just a quick insight. Today, Victor is going to share a little part of his expertise with us today. So that's going to be really interesting. Also with us, Serhii Malyi, and Serhii, our software architect. Yeah, hello, Serhii. Serhii has built his success with Apriorit, building up architectures for a lot of enterprise large-scale systems. So Serhii knows probably not everything. I mean, no one can know everything, but almost everything about driver architecture, kernel-level, can use myself. I'm program manager at Apriorit, projects related to driver and low-level development. I also projects related to reverse engineering and network management. And I'll be your host today. That slightly brings us to our today's agenda. It's coming up here, I think. Yeah, and today we, oh, sorry. Yeah, how many tries you need to open up an agenda? Yeah, finally, I hope you can see this. Please type, I don't know, equals sign in the chat if you see the agenda. Okay, let's proceed. First, we're gonna talk about our AI transformation journey. After that, we will discuss our AI adoption specific and how we adopted AI to our company processes and procedures. After that, we'll discuss our engineering framework and methodology around it, including some brief information about tools that we use, how we use them, and what we have to work with for AI and driver development. After this, we are coming to our probably the core part of our today's webinar, dedicated to our experience and expertise that we got during development of the drivers using AI tools. And to also we compare two approaches. The first one is traditional approach that we all used to do before this AI era, and to compare our results using different AI tools in terms of also business, technical things. We'll discuss some cybersecurity considerations, comparing all of them. Then, of course, we'll talk a little bit about supporting legacy systems. Actually, this is a quite also interesting and important topic, just because a lot of enterprises nowadays, they're running so we used to call it like a legacy infrastructure and legacy systems, and not because of they lazy or so on, not at all. Just because it is stable, it has been working for decades. All the customers and users are pretty comfortable with this, so that's pretty okay, and we need to take credit for this and also share our support to legacy systems as well. And then we, of course, discuss analysis and stability points, as I have mentioned already, some main cybersecurity considerations. And then we will summarize our results in impact and efficiency evaluation stage, which we made. And then we'll discuss summary, what we have nowadays, and how we should work with all of this. So let's start with our AI transformation stuff. And here, when we talk about AI or driver transformation, we aren't talking about writing simple scripts. We are talking about applying LLMs to low-level and kernel-level environments where there is no safety net, like, for example, managed runtime or garbage collector. In our core work with security critical components, just one mistake and the entire operating system goes down. So everyone knows it. And this matters really because we have reached a point where AI can help us manage the extreme complexity of modern hardware, whether it's parsing thousands of pages of hardware registers or identifying a synchronization flow that a human might miss during, I don't know, for example, 10 hours debugging, like a simple thing. AI has become a necessity for maintaining speed without sacrificing security. And during our AI transformation, we have moved beyond simple code completion to using AI for complex architectures and automated stability analysis. And AI acts as a second set of eyes here, really, for detecting race conditions, parsing hardware specifications, and so on. After talking about our AI adoption, we started adopting our processes. Let me think. Probably just for a couple of years already, when all of this AI started to come up. And we did it like everyone else with simple prompting, generating code, debugging, prototyping, and that's it. But very quickly we understood that the model itself is not the solution. The real volume comes from what we call so-called engineering system around the model, the harness, the tools, and the orchestration. So today we treat AI as a part of a structured workflow, not as a standalone assistant. And our process here evolved in 3 stages. This is experimentation, structured usage with proper prompting. And now, finally, it's a production workflows with validation loops, agent driver execution, and so on. So in practice, we use AI across the entire engineering lifecycle, from research and development to crash analysis, and even for reverse engineering. Yeah, by the way, regarding the reverse engineering, I have a question to our audience. Reverse engineering is a pretty specific thing to use, not to use, I mean to work with the help of AI. Yeah, so just interested and curious whether anyone uses any AI tools or approaches with reverse engineering tasks. Yeah, please type this in chat so we can discuss this in the end of our presentation. Okay, so talking about our AI, not AI, but yeah, engineering framework and its methodology, and we. From the methodology perspective, there are a couple of key patterns. The first is so-called context engineering, where we define architecture and constraints like kernel-level rules and even the role of the AI, for example, as a security reviewer or kernel engineer. The second is what we call agent-based development. And instead of one model doing like everything, we split the work into roles like planner, worker, and reviewer with clear tasks and validation. And finally, the most important concept is so-called harness approach. The model is just an engine, and quality actually depends on tools like debuggers, orchestration loops, and verification mechanisms. So we need to keep this in mind. Moving further and talking about tooling in context of our engineering framework, we combine different models like GPT and well-known Claude, depending on the task. Agent frameworks like OpenCode, for example, reverse engineering tools like Hydra, but with MCP integration, and debugging pipelines with WinDBG. And everything is built around simple principles like iterate, validate, and keep a human in control. So what I'm trying to state here for last probably almost 10 minutes already, we aren't just using AI for coding. We are building AI-powered engineer systems. So now let's proceed and dive deeply into a more technical part with our technical speakers here. And all I would like to add here that our technical part of the lecture will last approximately 30 minutes, I think. And after this part, we'll have room for answering all the questions our audience might have. So do not hesitate, type your questions along with our speakers in the chat, and we will handle everything after the presentation. So the chat is yours. And moving forward, we'll discuss and compare a traditional and AI-based approach for data development. So Victor, you can take a microphone.
Sure. Sure. Sure, I will do. Hello, everyone. And I will continue the presentation from here. And let's start from comparison between traditional approach and AI-based approach. So, as you all know, over last couple of years, vibe coding became a popular term. Like just the idea that just describing what you want and letting model to generate the code. And it works surprisingly well for web services, scripts, Python programming. But what happens when you apply the same workflow to Windows kernel mode driver? And in this session, we'll review a simple case of vibe-coded driver. We'll see what AI-generated driver got right, and more importantly, what it dangerously got wrong. So let's get started. But before we begin, we need to define exactly what we are comparing and what the traditional approach actually is. And this is my nostalgic slide here. And yeah, it shows Microsoft driver samples repository. And this is one of the most well-known starting points in Windows kernel development. The traditional approach is a combination of different moves. such as reading books and articles and from OSR online. If you work in this field long enough, you may remember it well. And use Windows driver samples as a source of inspiration, which means find this sample closest to use case, study it carefully, and use this information while building your own solution. There is also another way. You can try to adopt the sample for your needs as it is, but in this case, you inherit just a large set of structural problems. So I think nobody does like that. So mostly it's just a source of inspiration. And for most developers, this is obvious starting point. It's written by Microsoft, it compiles, it runs, it has been around for decades. And yeah, let's go further. Yeah. Just another slide about if you're not excited about previous one because it's just not informative. So this one summarizes and shows how it covers the entire ecosystem of possible driver types: general frameworks, audio, video, network drivers, USB drivers, human interface devices, storage, mini filters, everything. So it's huge contribution. And I made another one which implies that this is a really holy place of kernel mode development. Here we can see it handles all possible technologies like KMDF, UMDF, WDM, legacy drivers, samples for different trusted environments, see below, and a lot of different samples also. And one of the gems of Windows kernel mode development is file system stack, which also has strong support and deep coverage in WDK. Why I want to highlight it here, because of its importance for EDRs, AV vendors, and developers of security solutions. See monitoring and auditing here on the slide. MiniSpy is a canonical example of file system mini filter work. It demonstrates the filter manager registration pattern, post and pre-operation callbacks, communication ports. For a developer who is new to mini filters, reading MiniSpy is quite educational. That is definitely educational, I would say. Yeah, and yeah. And if you're already tired of its beauty and perfection, let's add some criticism and let's discuss WDK drawbacks using the example of MiniSpy sample, this particular one. The first notable point here should be that when developer first encounters MiniSpy C, they usually get frustrated, or I would even say screaming in pain. Just see the size of MiniSpy C as a single translation unit here. So 38 kilobytes, like a single file. All the logic, callback registration, IRP dispatch, communication port handling, log management lives in one file. This is okay because of MiniSpy is a sample, not a template. It's designed to demonstrate API usage, not to serve as an example of production architecture, but moreover. Then memory management. Sample uses pure C, no C++, no resource acquiring initialization, no destructors. So it's every allocation has a manual pair it free. Okay. Another one, global mutable state. So there is a simple global object accessed from every function of driver. There is no some encapsulation there, no synchronization, strict synchronization discipline. For a sample, it's okay. As a template for real product, it's a liability, definitely. Another one problem is a lot of defines, so it supports a lot of versions. It supports even Vista version, previous one. And conditional compilation pattern goes through this huge 38 kilobyte file. So it complicates, any move and any work if you want to do it with this sample. Any adoption attempts, for example. Yeah, so this table actually summarizes all the problems. You can read them also, and but there is important note here that none of these problems are bugs. These are just bad design decisions that affect code readability and maintainability. So this is not bugs. All bugs are already fixed. A lot of people already did tremendous amount of contributions there. So like huge thing. And let's look.
As one of our engineers says constantly, that another commonly cited Microsoft principle is like the best driver is still driver. So we probably must remember this always. So when you are able to implement some solution without a driver, so yeah, just go and implement it without a driver.
Yeah,
this
that's correct.
Won't be. Yeah.
I second this. Yeah, and the AI-based approach you can see on the slide is completely different. You just give a LLM model a high-level description of what you need, and somehow it produces a complete driver prototype. And this is exactly what our team did. We took a real security product use case, like EDR-style driver, and built it from scratch with iterative AI assistance. The driver we called protector driver intercept file input output process creation, registry operation, protecting specific assets from unauthorized access and modification. And it was developed through iterative AI assisted sessions, describing the goal, reviewing output, so pure vibe coding. This asking for corrections, sure, repeating, and but I think it demonstrates pure vibe coding session. Yeah. Okay, let's go. Yep. What we did. This slide highlights its architecture and shows common features and how communication and control tool is performed. The control interface uses 7 typed IO control operations: start, stop, add, remove process, status, logs, reload, and stuff. Hot reload is supported. Driver supports rule updates without rebooting the computer. Rules themselves are stored in the registry under file rules, process rules, and registry rules keys, which means they persist across reboots and can be updated by a management service without driver changes. Login, it has perfect login system. Login uses leveled macros, so yeah, and also it collects runtime telemetry, which is exposed by another IO control, and it looks like production credible architecture. I think so. Or production credible architecture as could have been 20 years ago, something like that. Because of, yeah, we'll check another slide as well. Yeah, this slide also shows the previous one, but is nice diagram. You can just see tool on the top and how it can get connected, and yeah, everything I was told earlier is nicely described here. Yeah, but some features which distinguish real security product and prototype were deliberately removed out of the scope, such as IO control drivers, IO control request signing. So currently, any process that can open the device can issue any command. it is better for product to have, signed IO controls with some payload, so that kernel should validate it with some asymmetrical encryption. And then there is no channel integrity, as you can see there. And as for communication channels, as for database. So we can say that entire cryptography thing is totally out of scope. Let's get, this slide shows side-by-side comparison between two approaches. Let's walk through this table. Yep. There are some categories here like code organization, login, and so on. So if you can compare what Minispy has, so we put like 38K characters in translation unit, and this is bad, obviously. Protector driver uses 8 focused modules, each with a typed header. This alone makes the AI-generated driver dramatically easier to maintain and extend. So it has a clean structure. It has nice login subsystem. It has good runtime configuration, so no hard-coded behavior, just it read the rules from registry, loads on demand. So, and code is easy to maintain and easy to read. So I would say on the architecture side, AI did very well. Let's look at the security side. Here. This is a slide where we should stop uploading. So it was very good, and see on this slide we can see why we should stop uploading here, because of it somehow wipe coded IO create device call, and if you familiar with kernel mode development, it's like a very bad decision because of IO create device with no explicit security descriptor, as this code does. In this case, the device object is created with default device security descriptor, which means world everyone. So if even non-admin can open this device and send commands to driver. This is like a big thing and very, very bad, maybe worst of wipe coded driver, one of the worst. Let me start from the gaps that Minispy covers, and let us look into Minispy, not into the AI generated driver. So this slide shows actually Minispy, and you can enjoy it. It's a raw beauty, and so it lines of code and huge this structure, and as you can see, it has a lot of if statements, like kind of a lot, and they are very confusing. But each one means something, and this one, for example, means transactional NTFS feature support. So what does it mean? There is a special component in Windows, half deprecated, as far as I remember, Windows Kernel Transaction Manager. It allows everyone to perform file operation inside a transaction. And I believe nobody uses them except ransomware and some bad actors. But the thing is, it's heavily used by spyware, ransomware, and stuff. And our wipe-coded mini filter knows nothing about transaction thing at all, at all. It's like it's bad. It has a lot of yeah.
Oh, sorry for interrupting. Just curious, are these mistakes commonly made by human? For example, if an engineer with not enough experience really or this is related strictly to the AI tools?
Sure. If you start, this is common problem if you start to build driver from scratch too. So if anybody starts and thinks like, oh, today is a nice, beautiful day, I will build my new driver from scratch, line by line without any additional sources, you will get absolutely the same. So
okay. But if I'm gonna take something from the Microsoft samples, I know that are not great, probably.
You definitely need to look into samples and at least for some unknown words for you. And another unknown word here is reparse tags. So reparse tag handling is an internal mechanism for symlinks, junction, cloud storage, placeholders, and this is a huge, I would say, path matching mechanism. And yes, our wipe-coded driver also doesn't have much support of it. So there is no, any ifs in this area, which is bad. So
okay,
it's definitely can be exploitable in this area. Another one just plain bugs, like there are a lot of ifs in mini filter sample, which are not like security ifs, I would say, security customization things, but some, for example, let's see at this slide. It's more subtle, but this is more can be dangerous also. So the correct behavior for mini filter is to check special flags in different operation callbacks, and mini filter does that well. So it checks special flag like post operation draining. Means like the volume is being unmounted and you just need to stop work and do not try to access some data of mini filter. So do not interact with mini filter more. And also this behavior is absent in wipe-coded driver. So it's more like it doesn't handle corner cases well, I would say, like this. Yeah, and here I put some nice summary table which describes our findings. Like it also summarize like previous slides. You can read this information and see it like there is an incorrect permission assignment for critical resource and not transaction support. And one bad thing also is it doesn't have memory mapped right coverage. So it's also, kind of huge thing which is missing. Yep.
Yeah, by the way, in terms of potential issues, I know personally several teams that use engineers just for writing code and AI just for reviews. So I don't think this is a viable approach, to be honest, especially for driver development. But on your experience, would you also have this, like, let's go to the bad section of the development approach, or that's totally fine?
Yeah, I think it definitely requires additional review, so we will check on some slides later. So thank you for comment. Yep, and so let's go to another table. Yeah, so there are just some plain bugs here, so it's not maybe not that critical. Not a major, but small bugs and some things that you definitely need to fix in production. I would say like that. Yeah. So this slide is why it is here, because of I just wanted to say that this is not a full scope. So previous table just highlighted major things, like big like entire missing subsystem support like this. And this slide shows like there are some also small things here and there. So it's not perfect, but it's okay. It works mostly. It works for most use cases. If you put some efforts and test it, you may conclude that mostly everything is okay. But there are some specific cases which are not covered or can lead to thoughts, for example. And this is kind of dangerous to deploy in production. This is why. So there are a lot of them. Yeah. Yeah. So let's, and this is the slide which shows what to do, what our conclusion regarding this experiment. Where does this leave us? And the conclusion here is not do not use AI for driver development. Now, the conclusion is use AI, but with your eyes open. And the most important thing is build the feedback loops that compensate for what it doesn't not know. So, yeah, here's the summary. First advice is train your agent and AI with domain-specific knowledge. Make sure the model has access to Microsoft driver samples, WDK documentation, known vulnerability patterns. The AI agent which has seen WDK samples behaves very differently from one working from the general knowledge alone. Then use AI as a reviewer, not as generator. After generating code, ask model to review it specifically for kernel security issues, access control, hierarchical constraints, re-entry hazards, time of code to time of use, and so on. So, use the power of LLMs to they are often better at reviewing than generating on these topics. The next important thing is AI is lazy, and AI is lazy as we showed on previous slides, but it is lazy unless you tell it not to be. Explicitly include requirements like follow kernel development best practices, ensure access control on device objects, handle all IRP types, including memory, mapped IO, and so on. So build good specification. Build good technical specification. If you do not ask, it will produce a working prototype that is not secure for all the cases. So just for some general, like common cases, I would say like this. Another advice is do not lose focus on classic attack vectors. First one is living off the land. Time of code of time of use. Build your own vulnerable driver. PID reuse. So there are a lot of attack patterns which are specific for kernel mode drivers. Make sure you review your driver exactly for them, because of there is a lot of. So let's go to another one item. Use external feedback loops. Write tests, write penetration tests, because of LLM is very good of writing tests and penetration also. Use MITRE attack website. So very special organization, you may know it, MITRE. And it perfectly it has perfect database of CVEs, and it has perfect database of common attacking schemes, and you can use it, and you could also train your agent with it, and you can go to GitHub. There are a lot of items which are published, some EDR, but just search for EDR bypass researchers. So in Twitter, usually, once in a week, there is some tweet that posts like, oh, I wrote another EDR bypass technique, and look at this GitHub perfect repository. So all these items can be your source of feedback loop. And yeah, and last and important one, keep your own expertise. AI doesn't replace kernel knowledge. As people say, AI is amplifier, so it amplifies it, and you just need to understand some things about Windows AI input-output subsystem, filter manager architecture, and common attack patterns to make sure your driver is okay and you can deliver it to production. And you need to understand it whether you use AI or don't use AI. The tool is as good as the engineer who work with it. So this is like my story today regarding this particular experience, but it's also summarize my view also. So I think AI, it doesn't replace traditional self-education even. You just need to build and maintain your expertise constantly in our security area. And yeah, this is everything which I want to say about this experience. And Serhii also wants to describe his experience. I think next.
Yeah, thank you. Thank you, Victor. I want to briefly describe some topics. The first topic Michael already mentioned. It's about supporting legacy systems. I just want to briefly describe why it's important, add some numbers. So according to the statistics, about 30% of all Windows users are working on deprecated systems. And if we are talking about number of devices, it's about 400 million devices of deprecated systems. And as you can see, most of them, thanks to the Microsoft, it's a Windows 10 that was deprecated last year. But it still needs support. It still have some functionality that need to be added. So that's why it's important task to support legacy systems. And in the context of support legacy systems, AI can help. I want to briefly describe where it can help. So, for example, if we are talking about legacy systems, we are talking about some deprecated technologies. And for example, if we are talking about Windows XP support, for example, for network stack, you will use probably some TDI technology that currently is deprecated. But if you want your driver to run on Windows 11, you probably will use WFP. And in this topic, AI can help a lot because it can summarize the technologies that developer can use. So instead of digging in a huge part of documentation of Windows samples from all of the last decades, you can ask AI to help you to identify technologies that can be used, for example, on Windows XP and, for example, on Windows 11, and it can speed up the work of development, the work of planning for your system. But of course, as any tool, you need to have your own expertise to know if you actually need to use some technology, and maybe you have some best approach, and you can, for example, modify the proposals that AI give you. The second problem that usually arrives when we are talking about supporting legacy systems, it's about APIs. So usually older systems doesn't have all the APIs that has newer systems, and if we want to implement some drivers that will work on a wide variety of systems, usually we need to have some compatibility layers. For example, the usual problem is about memory management in the kernel. If you are talking about some old systems and old kernel drivers, you will have some EX allocate pool APIs that used, and if you try to launch such a driver on modern systems, you will have an errors, and in this case AI can propose you some approach how to generate some compatibility layers, some abstractions to solve these issues. The next problem probably is also connected with API. It's about that old systems doesn't have all the parameters, for example, all the callouts, all the flags that has newer systems. And also, since AI is good in documentation, in parsing documentation, you can use AI to figure out what approach you can use instead of newer APIs. You can quickly find some approach, some solution for this case. And the last and but not the least, it's also about documentation. And as Victor already mentioned about, for example, about Windows driver samples, if we are talking about the samples, yes, usually if you work with them, it's very painful and helpfully AI can help a lot in it. So, for example, it can make a structure, for example, for some sample, can target you to the technologies that used. For example, why some ifs that Victor mentioned are used and why they can be helpful. So that's also a lot of help in development process. The case is another side. The case is that AI is not very helpful. It's about configuration of environments. So if you want to support a wide variety of systems, usually you need to have some old WDKs, so old IDEs. You need to have a bunch of old systems, and this is a task that cannot be fully automated, so you still need to manually configure much of these tasks. So AI can help here, but it can help to target you what VDK, for example, version you can install, and so on. The next issue Victor already described is about security. And if we are talking about legacy systems, usually the security is very important because on legacy systems, there are a lot of security issues. And if you are not thinking about these issues when you develop kernel drivers, you will have problems in the future. So in this case, as Victor mentioned, you need to use the techniques that Victor already summarized for development. And the last thing is about designing the complex systems. It's not so connected to kernel, but it's more connected to AI. So when the context for the task is very big, AI is not very good in it. And also AI doesn't know all your intents, it doesn't know all your goals. So to design some complex system, you need to have all the knowledge, you need to have expertise and knowledge that you achieve from your experience. So that's probably all that I want to say about legacy systems. And the next
move forward, what do you mean by legacy and old systems, by the way? Just was curious, because whether it is Windows 10 or Windows XP, I don't know.
For now, it's Windows 10 also, but probably if we are talking about very legacy, maybe it's, for example, Windows Server 2003 or something similar. So such a systems are still supported, and there can be tasks to support such systems.
Yeah, I know the 2003 is supported nowadays still. Yeah.
So the next topic that I want to describe and that is connected to implementation, it's about debugging. So if we are talking about debugging of kernel drivers, everybody who works with kernel knows what is WinDBG and knows how to work with it. And usually it looks like you work with some terminal from late 19th. You need to write some big commands with a lot of parameters to get some addresses of structures. You need to have a calculator to convert some hex integers to figure out some address in memory and so on. So usually it's not very easy to debug it, to debug the kernel. And in this case, AI is helpful because nowadays there are many tools that can help to connect such tools like WinDBG or CDB to the AI. And nowadays, if you connect such a tool, the work will become not like writing very big commands in the chat, in the command line, but with prompting AI to give you some information about some structures, about some, for example, stack frames and so on. So here you can see some of them, like MCP, WinDBG, Copilot Agent, and so on. The most of the tools work as MCP servers, so they just connect your AI to your tool, and you can work with it. When we are talking about connecting AI to the kernel, it usually leads to the problem that if you have, for example, some crash dump from your customer system, the crash dump can have some sensitive information, and it's not very good to give such sensitive information to the cloud. And to fix this issue, there are several approaches. The first, maybe the obvious approach, is not using such a tools and using AI like a chat. So in this case, you fully control all the data that you pass to the AI, but it's not a very perfect approach because it's very slow. You need to copy paste the data from AI chat to WinDBG and so on. So then second approach that we can use, it's use some filtering. So in this case, we can use a local LLM as a filtering layer, so we can configure it to filter out all the sensitive data that WinDBG can return, and only after filtering we can send all this data to the cloud, to the AI that will process it. And the third, maybe the most secure approach is to use all the stuff locally. So to configure your local LLM to work with your WinDBG. In this case, no data will be sent to cloud. But the only drawback here is that you need to have a powerful hardware to be able to analyze your data from WinDBG. Want to share some knowledge what we get when we work in with AI with debug. For the issues that AI can help, it's for example, issues with double memory freeze, issues with some referencing of freed memory, or for example, some simple memory or resource leaks. AI is very helpful in these cases, and for example, it can be automated to analyze some crash dumps, and in simple cases, it can target to the problem, it can write where the problem is and how potentially it can be fixed. But if you are talking about more complex issues, for example, like some complex deadlocks for complex systems, or for example, some memory corruptions when we have multiple drivers included in our system, it's not very useful, and you still need your own expertise to it. So in summary, AI in debug process nowadays is helpful. It can help you to work with old tools, but as I said before, you still need your own expertise to it. So probably that's all that I want to say for this topic. Michael?
Yeah, thank you, Serhii. Yeah, actually, our technical part of our webinar is almost complete. Actually, yeah, but I just wanted to take a moment and to summarize some critical aspects, really, from the cybersecurity point of view. Well, regarding the cybersecurity considerations, these points were here already, but I would like to summarize them because they're way too important. So we need to define actually 4 main domains where AI usage meets kernel requirements. So it is IP leakage and data privacy. It is vulnerable code generation. It is securing the crash dump pipeline, which is very important. And of course, it is so-called AI supply chain. This is about evaluating the risks of outdated knowledge and legacy patterns. Now let's take a bit closer look to each of them. And talking about the intellectual property, for example, when you feed proprietary driver code into a public model, you risk that the logic becomes a part of a future training set. Pretty obvious. But to mitigate this, engineers must utilize so-called zero data retention endpoints. And our focus here isn't just like don't share these secrets. It should be establishing of formal governance policy where the sensitivity of the architectural context is addressed before any prompt is sent to the cloud. Moving forward to the next one, it is about, let me double check, it is sliding up. Yeah, it's about checking the analysis of vulnerable code generation. So AI suggests design patterns that are perfectly safe for user mode applications, but they risk and doesn't work simply to the kernel mode environment. And a model might suggest, for example, a blocking operation in the context where it is strictly forbidden, and so on. So it's leading to deadlocks or system crashes and stuff like this. And here we must just treat AI generated code as untrusted input. So that requires a deep dive architectural audit before any type of integration. Moving to the third aspect here. So when we automate crash dump analysis, we encounter a significant data privacy challenge. Dumps are essentially a snapshot of system memory. So this often includes sensitive tokens or user data. And to safely use AI here, you must implement a sanitization pipeline. This involves stripping so-called personality identifiable information and masking encryption keys before the data reaches the model. This should be noted. And the goal is to provide the AI with just enough context to identify the root cause without exposing the underlying sensitive data. And talking about our AI supply chain, so we have to know that because a lot of models, probably, no, not a lot, but each model, SRL, is trained on historical data. They can be biased toward legacy patterns. In kernel world, what we consider a standard, as in the case with Victor, who mentioned this already. So what was considered a standard like 10 or 20 years ago, right now might be a critical vulnerability. So whether it's weak, cryptographic, and so on, the engineer must act as a knowledgeable filter. So I'm noting this one more time, that ensuring that the AI's output relies on modern security standards. It's very, very important issue, and everyone should take this into account as well. Well, and now let's finally talk about our business impact and efficiency. So here we compare three main engineering paradigms. So they're pretty simple and straightforward. One of them is just human-only development. So this is our historical baseline, which we compare everything with. But this model is highly deterministic, and it is bounded by a speed of natural and manual work. Talking about fully AI-driven approach, we evaluated the feasibility of completely autonomous code generation on kernel space. And in user mode or standard web application development, such approach really can be successful for us. But however, in kernel development, complete autonomy breaks down due to the model's lack of live execution context. So repeating all the mistakes and bad practices that we previously mentioned. And like the golden middle here is the human plus AI approach. So this represents a collaborative framework between human and AI tools. In this model, the speed of development really increases according to our metrics, and the system stability is maintained because every line of the untrusted AI code is audited before compilation. So this lesson here, the lesson here is pretty clear. So the maximum optimization point is not found just by replacing a human with AI, but by collaborating with AI automation tools to minimize manual routine overhead. Going further to our what we have gained after our experiments. So we can represent just three different metrics to make sure we have a clear objective, clear objective view on the things. Regarding the development speed, the most visible impact of generative AI is the acceleration of the initial phases of development. And by delegating high-volume data transformation, for example, like translating hardware specifications into valid C headers, the timeline for structural prototyping is really lower. And it is critical to measure this metric across the entire development cycle. Any time saved by code generation can be quickly lost in code reviews and the engineer must debug all of the AI flows, for example. So this is like a usual case. Regarding code quality, this is a bit more interesting because quality metrics really improve dramatically only when the human engineer enforces strict context limits, directing the AI to modular structures rather than allowing it to make changes, complex logic, automation, and so on. And finally, regarding the security improvements, so this is the core thing which we noted really. This metric demonstrates that AI acts as a powerful force multiplier for early stage defense. And when embedded as a static analysis layer, generative models are great at catching common implementation oversights, such as incomplete error handling path and so on. And it does it even before the code even reaches a hardware environment. So this is very important. And finally, these metrics show us that the optimization in kernel space is nonlinear, really. So the goal is to maximize velocity in the automation heavy phases so that the human engineering capital can be used to what matters most: architectural validation and security auditing. And just remember that AI with human speed for the whole SDLC doesn't have a winner. AI is boosting code quality and security. And just remember that AI and human, this is not a competition. This is a team, or a great team if you set up everything properly. Okay, thanks for your time and thanks for your attention here. I see that we have already a lot of questions and notes in our chat. So let's handle them one by one, probably. Okay, I'm sharing the first one. Hopefully you can see this on your screen. Yeah, and the first is a question from Ryan, and it is: how consistent are the results you are getting from AI in driver development? Do you see a lot of variability in outputs? And if so, how do they deal with that? Have you developed any prompting patterns that make results more predictable? Yeah, I think, Victor, you can help us with this.
Yeah, sure.
Yeah.
Sure. There is a certain level of variability, I would say, because of, as we saw, AI model usually even tries to, it has some pattern which describe particular user who asks a particular question. And then AI model tries to handle the request in a way it fits just for this particular user. So if it thinks that currently is a security expert is asking about something, it will usually increase some, do some efforts and provide more secure output. This is like a mirror. So there is so yes. And how to deal, like everybody. So how to deal with it? So driver development differs a lot from user mode. So there are a lot of things, but programming with AI is no different in this area. So how to deal with it? You need to good specification. You need to involve AI into the testing, into different activities like organize feedback loops between agents. You need to actually use skills and share skills. So if you are familiar with AI, boom last all like a year or another year ago, like a lot of people, they constantly are writing MD files which describe different skills for AI agents and AI models. There are some special, for example, Claude MD files for project which helps AI to get the necessary context. And this is like similar thing to if you want AI to write code according to some coding standard in user mode. It reminds me of this. So in kernel mode, there are also some standards, but they are wider maybe and more security focused and so on. So this is like this.
Yeah, thank you, Victor. I think this is a great answer. Also, we have a couple of notes from and the first note, it is about that important to work iteratively and to check and integrate as you go. Use dev, sec, ops, etc. in your build chain. Yeah, this is a great thing to know. So yeah, let's put some attention to this. And another note is that typically AI can do small work in depth on function level or broad scope approach for structure, but typically not both. Yeah, I also can agree with this. Yeah, and it makes perfect sense for me. So I don't know, maybe Victor or Sergey have any comments about this, but I think this is like
yeah,
sense.
This is exactly. This corresponds to my point that AI is very lazy. He's not lazy, or maybe it's just like of the thing that limits its power because it cannot produce 300 pages for any request. So this is why it really needs to focus on some general and like backbone, on some core scheme, and then and this means it just should skip all the small details. Yeah, absolutely correct.
Yeah. And the next one, we have question that typically we need some older complete systems to do these kind of work for testing and etc. How do you handle the need for having compatible hardware on hand? Yeah, this is a very interesting question. Hope I understood this correctly. But from a business perspective, we just, when we need to develop some driver for an older system, we start establishing connection and communication with the owners of these systems, for example, or with a manufacturer who might have a specification, for example, or who might have some older devices to ship us post. So that's how we usually approach this. Also, you are able to make some emulator for the device if you're having the specification. Also, sometimes we are utilizing our reverse engineering skills just to understand the inside hardware communication, how this device works, which protocols they're communicating with, and so on. And this way we can emulate it also as plan B or even plan C. But the first thing we will do here is just to find a real prototype of this device. Usually it is possible to find it somewhere. So if I understand your question correctly, Tom.
I can add something regarding it. So in some cases, if we talk about Windows programming, we just have all necessary stuff because we are doing it for like 20 more years. And this is why we just have necessary WDKs, we have the systems, and we have experience of having such laboratories and so on. So in this particular case, we don't need to communicate with some vendor because we already have everything we need.
Yeah, I agree. This is probably the most positive scenario for us when we do not need to look for anything. Okay, we have next question from Mary. And where can AI realistically reduce project time? And where does it usually create additional validation work? I would say it depends on the task, really, because as we mentioned in our presentation or lecture, that AI does best, for example, for some routine work, when you need to do a lot of so-called mechanical work during development, or when you need to parse some hardware registry table and make it look so it can be used from the C code in the view of headers and so on. So this way can be automated from some point, and this reduces development work really. Also, there are some tasks probably that you might assign to AI as to an engineer, which you need to review this after AI. So I would really depends. And of course, where AI usually creates some additional validation work. In general, is probably in driver development when we talk about some validation. So if you ask AI, as we mentioned, for example, to create an architecture, so we really need to do, I would say, a good reviewing work. Yeah, just because AI may make some classical mistakes, which are also okay for some engineers of the entire level, for example. But we need to validate code that we do not know actually. And we need to validate architecture, which we didn't create yet. So this, I would say, the main pitfall when we are working with AI. But when the process has been established properly, so integrated into your workflow, you may just force your development in terms of the whole SDLC without a problem. This was from my management point of view. Sergey, Victor, maybe you have another opinion.
Yeah, I can add just that the answer is a part of the question currently. I do like the word validation here, and it somehow answers this question well, because of each task. For example, if you have some task and you want to give it to AI, you can imagine how you would verify it. And if the verification cost is very high, and is more than, do it manually, then you lose. If you do some task which can be easily verified, you will win. So it's for example, one of criteria which you can use for somehow planning your AI interaction and for making it more realistic and more, efficient. There are some tasks which AI does great, no matter it is kernel level or user level, because of it does prototypes, creates prototypes very great, very fast. And if you need to do some prototype and just test something, you'd better use AI for that. Then there are some tasks like writing tests, writing even penetration tests also. It can be very fruitful to use AI, and it can speed up you. And you can easily test this work. So it doesn't require you to go even line by line and deeply inspect the system. There are some tasks which are completely different, and you really better know every line of your code before pushing it to production. And this means somehow you need to have some feedback loop, and you need to put into this feedback loop or developers, other AI agents, or so on, or maybe tooling. So it's like, this is the development how it looks today.
Yeah, that's totally correct. And on the last point, we have another input from Tom. Tom is our most active user today. I mean, most active listener. And these are things you learn from when you're using AI, in contrast to people who cut and paste posts from AI. Great job. Oh, thank you, Tom. Yeah, we're really happy you enjoyed it. That was our initial goal. Yeah, so thank you. And thank you for your notes and questions. They are really great. Okay, it seems that we don't have any questions so far. Yeah, and one more time, I just would like to thank everyone who found this possibility today on Thursday to join us to be the part of the AI discussion around the driver development. So we appreciate your effort on Thursday. So yeah, it was great. And thanks for your time and thanks for your attention. If you have any further questions after this I know, complex topic. So there are our contact information on your screens. So you can just reach us out like anytime you wish, and we'll do our best to help you and to help you figure out with everything you have around cyber development, especially. Okay. Also like to thank speakers, Serhii, Victor. Thank you.
Thank you.
Thank you.
My pleasure.
Yeah.
Have a nice day.
Yeah, likewise.